Another reason that we care about the shapes of molecules is to be able to understand whether a substance is polar or not. Now, we've talked already about bond polarity. Let's review that a little bit. When you've got two atoms that are bonded together, here's the Lewis structure for hydrofluoric acid. When you've got two atoms that are bonded together and their electronegativities are much different, where this is all one word, the electronegativity for H is 2.1 and the electronegativity for fluorine is 4.0 if I'm using the Pauling scale. And I can see that those electronegativities are very different. Remember what electronegativity was. It was a score that told you how greedy that atom was for bonding electrons. The fact that this one's got a 4 and this one's only got a 2.1 means that this fluorine is going to be grabbing on to those bonding electrons more tightly than the hydrogen does. There's a tug-of-war for the bonding pair, and the fluorine is going to be winning it. Now, what that's going to do is make this end of the molecule negative, and we say it has a partial negative charge on this end and a partial positive charge on this end. We're using this Greek letter delta for the word partial. Partial negative, partial positive. So that's a polar bond. It has a positive pole on this end and a negative pole on this end. And we sometimes will draw a little arrow next to the bond that looks like this. It goes from the positive to the negative. It points towards the more electronegative atom. And this little arrow is called a bond dipole. It is easy for us to do experiments that measure bond dipoles. So it's an experimentally measurable thing that we have. We can tell that that is a polar bond, and that this will overall be a polar molecule. Now, how can you tell when you have a polar bond? Well, it'll be a polar covalent bond, remember from worksheet 4.1 that we did quite a while ago now, that if you've got two nonmetals bound together and they have different electronegativities, you have a polar covalent bond. So you'll have a bond dipole in that case. Now, some bonds are polar but not very much. If you have a carbon-hydrogen bond, hydrogen has got Pauling electronegativity of 2.1, and carbon has got a Pauling electronegativity of 2.5. So there is a difference in electronegativities here. This will be the negative end of the bond, and this will be slightly positive. But it's a very small bond dipole. So you don't have very much of a bond dipole here, and a lot of substances that have got only carbon-hydrogen bonds in don't have much polarity at all. So this would be high polarity, and this would be low polarity. So it is not really a black and white thing. There are a lot of shades of gray in polarities for bonds. Now, here's where molecular geometries come into play, and this is one of the things that we are going to apply molecular geometries to. It doesn't matter that something has a polar bond. It matters how the polar bonds are arranged. Let's look at a carbon dioxide molecule. Here's the Lewis structure for carbon dioxide. And I want to ask, is this a polar molecule or not? Now, I've got, I can look up the electronegativities for these. Carbon has got an electronegativity of about 2.5, and oxygen has got an electronegativity of about 3.5. So there's going to be a bond dipole that is going to go this way. It's going to point from the carbon to the oxygen. But now look, there's another bond dipole that points the other way. Now, if this was a cart and this was a horse, this would be pulling the cart this way. But attached to the other end, there's another horse of equal strength. So they're pulling against each other, and the bond dipoles are going to cancel in this molecule. Now I know this is a linear molecule. We've done it a couple of times in previous videos. So I know that these two are going to be pulling against each other. And I would say this is a nonpolar molecule. Now, in general, I'll give you a general rule that's based on what we saw here. Any geometry that attaches the same thing to all arms on the central atom is nonpolar, because of this effect that we were talking about here. All of the bond dipoles will cancel in this situation. So let's look at some examples of that. If you've got CH4, there's the Lewis structure for CH4. What's the electronic geometry? It's got 4 clouds around it, so it's going to have a tetrahedral electronic geometry. And it's got the same thing hooked to every arm on the central atom. So this will be nonpolar. What if I have NH3? That's ammonia. Here's the Lewis structure for NH3. What's the electronic geometry on NH3? Well, it's got 4 clouds around it, so it also will be a tetrahedral electronic geometry. And it's got a lone pair up here on top, and it's got a hydrogen here, a hydrogen here, and a hydrogen here. So it has something different attached to the central atom, something different from the other 3. So it will be polar. Now, if you use this rule, you can recognize a lot of nonpolar molecules, and you can recognize a lot of polar ones too. This rule alone will let you classify most simple molecules as polar or nonpolar. But you know, things are not always so easy, right? Let me give you some exceptions to that rule. Suppose I have a trigonal bipyramidal molecular geometry that looks like this. It's got the same thing on the poles, but different things attached around the equator. So here's the equatorial positions, and here's the axial positions. Now remember that you can think of a trigonal bipyramidal shape as a combination of 2 shapes, a linear shape around the poles and a trigonal planar shape around the equator. Now if you look at those 2 shapes separately, the linear shape has the same thing on both arms, and the trigonal planar shape has the same thing on both arms. So this turns out to be nonpolar, even though it has different things attached to the central atom. So it is an exception to that rule that we just put a box around. You can think of some other ones too. Remember, I was talking about the square planar molecular geometry. Anti-cancer drugs called cisplatins have this molecular geometry. Now it's got different things that are attached around the central atom. So you might guess from that rule that it was polar because it has got something that's different from something else attached around the central atom. But look, the dipole for the lone pair, and lone pairs do have a pole. They have a sort of a bond dipole, but that one is going to cancel out that one. And these are all going to cancel out each other. So this one also will be nonpolar. So sometimes you can have symmetry. You can have a relationship where you have a balance. The structure seems kind of balanced. And we'll call that symmetry. That usually makes things nonpolar if you have a high degree of symmetry like that. Polar. Let's look at some more subtle examples of deciding whether you've got a polar molecule or a nonpolar molecule. Suppose you had this multi-center structure. And you want to decide if this is polar or not. Now, think of the little tugs on the bond dipoles. The chlorine is a very electronegative atom, so a bond dipole is going to be tugging that way. Here, this bond dipole is going to be tugging in the opposite direction. And you'll have a small bond dipole that tugs that way, and a small bond dipole that tugs that way. Now you can see when you draw these in that this one is pulling against this one, and they're both exactly the same strength. And this one is pulling against this one. These two are pulling against each other as well. So you have symmetry here, so this is a nonpolar molecule. Now suppose I give you one that's very similar to that. We are going to see in the next couple of worksheets that when you have a multiple bond, it can't spin. You can't spin around that bond. Now let's draw the bond dipoles in. The chlorine is more electronegative, so it's going to be pulling up that way. This chlorine is going to be pulling up that way. And this hydrogen, the bond dipole is going to go like this. It's going to be very small. And this bond dipole is going to be very small. So we have a big bond dipole pulling up in that direction and a big one pulling up in that direction. Are these two going to cancel each other out? No, because they're both pulling up. They're both pulling in this general direction up here. So they're not balanced. They're not canceling each other out. These are both pulling up in the same direction. They're pulling with each other, not against each other. So this will be polar. Now, if you understand these examples and these exceptions, and if you have this rule for all the other cases, you should be able now to predict whether or not a molecule is polar or not by looking at its molecular geometry and drawing little arrows for the bond dipoles. If the bond dipoles are pulling against each other and they're all of equal strength, then it's going to be nonpolar. If the bond dipoles are, it's going to be nonpolar if they're all pulling against each other and they're of equal strength. If they're pulling against each other and they're not of equal strength, then it's going to be polar. If they're pulling with each other, then it's going to be polar.